guys. I'm Dhruva Juloori from Uber's developer platform. Uh, my work primarily focuses on handling continuous integration at scale, especially in large-scale developer environments with high commit velocity. Today, I'm here to share some insights about how do we handle continuous integration at Uber and share some of my learnings. Before diving into the topic, I would like to give some context about monorepos. Most of you might be already familiar with it, but yeah, just to give some context, monorepo is a single and shared source of repository that hosts all or most of the company's assets. Instead of splitting projects into multiple code bases, everything is hosted at a single place. The advantages of monorepo are studied widely in software engineering community. Some of the key advantages are it's easy to ensure code consistency and standardization, simplify dependency management, and also it also greatly improves the code shareability and reusability. Some of the leading tech companies use monorepos as their approach to host their code bases. So, starting with the first principles, what's the problem? And why is maintaining a green main line a hard? So, let's take an example. So, the figure what you see is a main line of a repository, and currently it's all green, meaning that all build steps are passing. But there are two developers, Alice and Bob, create new branches based out of same reference point to introduce their respective changes. Alice introduces his change C1 and Bob introduces his change C2. Now, both of them test their changes individually. All of the build steps pass. LS tries to merge his branch to the main line. Main line is still green. All the build steps pass. But when Bob merges, the main line breaks. Because Alice and Bob have tested their changes individually but not collectively. Now just imagine what could happen at scale. So at Uber scale, we have about 4,500 plus engineers working from 10 plus global development centers, concurrently committing to 6 of our monorepos: Android, iOS, Go, Python, Web, and Java monorepos. Our monorepos handle changes about 65,000 plus per month and are home to 1,000 plus microservices and facilitate about 100,000 plus deployments per month and host about 130 million lines of code or even more than that as we are speaking. So let's talk about the drawbacks of a red main line. So the first one, so the main line being red directly impacts the business in terms of cost and also time. So the first one is delayed rollouts. So if your stable branch is not in a stable state, the release of new features or patches may get delayed, which could directly impact the business in terms of cost. And the next one is hampered productivity. The developers might not be sure of like why their changes are failing in CI. Is it because of their change or something else? And of course, when hundreds of engineers are concurrently committing, so it gets very hard to restore back to the last known stable state. So no business wants to be in this state. So how do we solve them? Let's meet submit queue. It's essentially Uber's merge queue. It guarantees or it provides an illusion of a single queue to the developers to submit their changes. It guarantees reasonable SLOs for developers to land their changes quickly. It utilizes CI resources very efficiently. And of course, it always maintains green main lines even at thousands of changes per day. So how do we do this? In a nutshell, submit queue broadly consists of 4 core components. The first component being enumerator. It basically takes the queue of pending changes and builds a binary decision tree of all possible builds for those changes. Second one being the profiler. The profiler takes these binary decision trees, aka speculation trees, as an input and ranks the changes according to the landing order based on predicted build times. Then comes the prioritizer. It computes the probability for all of the nodes to schedule these nodes as a builds based on the landing order information and also by predicting the change success. Next, the selector. The selector basically selects the top uh, set of probability nodes and then schedule those nodes as builds in the CI. Now let's take a practical example and see like how all of this fit into by taking three simple changes as an example. So let's say there are three changes: C1, C2, and C3 arrived in the order mentioned. So for C1, you only need one build. So you just need to build C1 in order to make a decision whether to land or reject. So the possible build for C1 is only one, which is B1. Now for C2, since it has arrived after C1, the total possible builds are 2. So C2 needs to be tested with C1, and also in the cases when C1 doesn't pass, so which is like C2 needs to be tested with the stable head of the main line. Now for C3, there are 4 possible builds because C3 needs to be tested with C1 and C2, and also in the cases when C1 and C2 fails. So in this fashion, like the tree grows exponentially. So for n changes, we need 2 power n minus 1 builds because this is essentially a perfect binary tree and resources are very limited and very finite. So is there a way for us to do better? So then comes the concept of conflict analysis. Until now, like we assume that all changes conflict with each other. So basically, we need to speculate all of them together. But what if we could prove that changes can be independent, or changes are independent? So how do we do it? Like we do conflict analysis by leveraging the build system. So the intuition behind conflict analysis is like 2 changes are said to be independent if they affect a disjoint set of build targets. For example, there are 2 changes C1 and C2. Now just apply those 2 changes separately on the head hedge of the main line and compute the build target hashes. Now if there are any overlapping build target that have been changed between these 2 changes, it means that they are conflicting, otherwise they are not. So let's take an example of conflict analysis. For example, in this case, C2 and C3 don't conflict, but they both conflict with the chain C1. So the total possible builds are 5. Like C2 and C3 need to be tested with C1, but C2 and C3 need not be tested collectively because they don't conflict with each other. So in this case, the total possible builds are 5, but in the previous case, the possible builds were like 2 power 3 minus 1, 7. So we reduce the possible builds by a factor of 2. Now just imagine like what could happen at scale. The second example where C1 and C2 don't conflict, but C3 conflicts with both of them. The conflict, so the speculation tree looks like this. So the total possible builds are 6. So in this case, the changes C1 and C2 can be committed in parallel, but C3 has to wait until we know the decision outcomes of chain C1 and C2 because it is conflicting. But still, we reduced number of builds by a factor of 1 for 3 changes. But as the size of the changes increase, like we could see a lot of reduction in number of possible builds. But there could be a cases where there are actually conflicts. So at scale, like when there are like hundreds of developers concurrently committing, like there are high chances that a lot of changes conflict with each other. So what do we do like in those cases when there are actually real conflicts? So here comes the concept of probabilistic speculation, where basically we try to compute the probability of build needed for each node, and then based on that, we make a decision to either schedule that build and either schedule that node in the build system as a either schedule the node in the build system based on the resources available. So for example, let's take this simple speculation tree like for 3 changes. So for B1, which is essentially building the chain C1, the probability needed would be 1 because there's only one possible build for chain C1. So the probability of build needed for B1 is 1. But for B12, the probability of build B12 needed would only be dependent when the build B1 is successful, which is nothing but the chain C1 should be successful. So the probability of build needed for 1-2 is nothing but the probability of success of C1. Conversely, the probability of build needed for B2 is basically the probability of failure of C1, which is 1 minus probability of success of C1, because the total probability is always 1. In this fashion, we could try to compute the probabilities of each build needed and come up with certain values. But there are certain challenges. For example, let's say C1 is a very large diff, like which changes a large set of build targets. And then there is a change C2, which only change like a small subset of build targets. So now what happens is the build B1 is still building, but the change C2 builds have already been finished. Even though the change C2 builds have been finished, it has to wait because the builds of B1 are still in progress and C2 is conflicting with C1. In the similar fashion, when C3 is conflicting with C1 and C2, and C3 being a very trivial or a small diff, and C1, C2 are like bigger diffs compared to C3, all of the speculative builds of C3, since they have finished, even though it has to wait, because the conflicting builds ahead are still in progress. So this could be expensive, like, and there is no reason for us to wait. Like, if we could determine change is safe to land. So basically, if you look at last two examples, so in this case, like the builds of chain C2 have been finished in the CI and yielded same outcome. And in this case, the builds of chain C3 have finished in the CI and yielded the same outcome. So it's basically there's no reason for us to wait or block these changes by to land. So as the wait time increases, the chances of conflict of these changes with the future changes also increase, which ultimately blows up the speculation space and the number of possible builds. We don't want that. But if you carefully observe, so C3, as in this case, C3 has been evaluated with all the possible builds of C1 and C2, so we could safely land C3 because the state of the main line when C3 has landed first and then C1, C2 would be just as equivalent to the state of main line when C1, C2 has landed first and then C3. It's just an application of commutative property, like A plus B equal to B plus A or A into B equal to B into A. So now, just scaling this concept to multiple concurrent changes, we could derive a following insight. Basically, what it means is changes can be landed faster if all the speculative builds with conflicting changes ahead are evaluated and yield the same outcome. This is what we call as bypassing large diff. So now coming back to our probabilistic speculation, so the goals of this model, or the way we try to compute the probabilities, are like we prioritize the speculative builds for all the changes that can possibly bypass its conflicting changes and land faster, and only prioritize the most likely builds for the changes that cannot bypass, so that we are using resources very efficiently. Now, taking these two goals and putting into a mathematical notation, we derive the following formula. So the probability of build needed is nothing but depends on two things: the probability of the build outcome of the conflicting changes ahead, and the ability of the respective change to bypass its conflicting changes ahead. So now the next question, like how do we evaluate the build outcome, or like the finish times, or like the build times? Of course, like we use machine learning to predict the change success and build times. So we use classification and regression models for predicting the success of the change and predicting the build times. So our feature set includes approximately about 50 plus features, and our prediction accuracy is about 97% for our classification model, and mean absolute percentage error is about 5 to 7% for our build time prediction model. And we have our each monorepo as its own model. So some of the key features that we use for our prediction models are like characteristics of a change, like number of build targets, number of change lines, number of added files, and status of pre-submit checks, lint checks, etc. And some of the dynamic speculation features include like how many builds we used, or like number of builds that have actually failed, or number of retries, etc. So now, jotting all of this together, so the way submit queue works is like, as I mentioned, like there are only 4 core components. So a developer submits a change through an API service, and then an enumerator takes all of these pending changes and builds a binary decision tree of all possible builds by leveraging a build system and doing conflict analysis. And then the profiler, which ranks the changes according to the landing order based on predicted build times using build time analyzer. And then comes the prioritizer, which computes the probability of build needed using the landing order information, and also by predicting the change success. And then the selector, based on resources availability, it schedules the nodes in the CI, which has like high probability values. And once the CI builds have been finished, it makes a decision either to commit or reject the change. So submit queue has been in Uber for a while, probably from the tail end of 2018, and our recent algorithm changes and new introduction features include like bypassing large diff and build time prediction. After introducing these two features, like we observed a significant gain in terms of resource usage and also the CPU consumption and the wait times. So approximately we saw like a resource usage of 53% reduction in three of our major monorepos, Android, iOS, and backend Go repo. And then CPU consumption in CI reduced about 37%, and waiting times have improved by about 45%. Yeah, and these are some of the resources that we have published in some of the conferences, and also some of the blogs we published. Feel free to check out. And yeah, that's about it. Yeah, if there are any questions, like I would be happy to answer. And for any discussion with regards to continuous integration at scale, yeah, my DMs would be always open, and now open for questions if there are any.